An image depicts three tan squares, lying side by side along the upper left corner. Two of the same squares also lie side by side in the lower right corner. Each square has a black dot in the center. One of the squares is labeled CO subscript 2 and has a double-headed arrow pointing from it to a red tube-like structure that runs between the squares across the image from the upper right to the lower left. This arrow is labeled CO subscript 2 dissolved in plasma. The red tube has two round red shapes in it, and the upper one is labeled CO subscript 2 carried in red blood cells. The gaps between the squares and the red tube are colored light blue. One of the squares along the top of the image is labeled CO subscript 2 and is connected by a double-headed arrow to an equation in the red tube that is labeled CO subscript 2, a plus sign, H subscript 2O, right-facing arrow, H subscript 2 CO subscript 3, right-facing arrow, HCO subscript 3 superscript negative sign, plus sign, H superscript positive sign. The compound, HCO subscript 3 superscript negative sign, is then connected by a double-headed arrow to the space in the red tube and is labeled HCO subscript 3 superscript negative sign dissolved in plasma as carbonic acid. Figure 13. One transport of carbon dioxide in the body involves several reversible chemical reactions, including hydrolysis and acid ionization, among others. Chapter outline. 13. 1. Chemical equilibria. 13. 2. Equilibrium constants. 13. 3. Shifting equilibria, Le Chatelier's principle. 13. 4. Equilibrium calculations. Imagine a beach populated with sunbathers and swimmers. As those basking in the sun get too hot, they enter the surf to swim and cool off. As the swimmers tire, they return to the beach to rest. If the rate at which sunbathers enter the surf were to equal the rate at which swimmers return to the sand, then the numbers, though not the identities, of sunbathers and swimmers would remain constant. This scenario illustrates a dynamic phenomenon known as equilibrium, in which opposing processes occur at equal rates. Chemical and physical processes are subject to this phenomenon. These processes are at equilibrium when the forward and reverse reaction rates are equal. Equilibrium systems are pervasive in nature. The various reactions involving carbon dioxide dissolved in blood are examples. See Figure 13. 1. This chapter provides a thorough introduction to the essential aspects of chemical equilibria. Learning objectives. By the end of this section, you will be able to describe the nature of equilibrium systems. Explain the dynamic nature of a chemical equilibrium. The convention for writing chemical equations involves placing reactant formulas on the left side of a reaction arrow and product formulas on the right side. By this convention and the definitions of reactant and product, a chemical equation represents the reaction in question as proceeding from left to right. Reversible reactions, however, may proceed in both forward left to right and reverse right to left directions. When the rates of the forward and reverse reactions are equal, the concentrations of the reactant and product species remain constant over time, and the system is at equilibrium. The relative concentrations of reactants and products in equilibrium systems vary greatly. Some systems contain mostly products at equilibrium, some contain mostly reactants, and some contain appreciable amounts of both. Figure 13. 2. Illustrates fundamental equilibrium concepts using the reversible decomposition of colorless dinitrogen tetroxide to yield brown nitrogen dioxide, an elementary reaction described by the equation. Ento 4, letter 1D4542, note 2, letter 1D454. Note that a special double arrow is used to emphasize the reversible nature of the reaction. A three-part diagram is shown and labeled A, B, and C. In part A, at the top of the diagram, 3 beakers are shown, and each one contains a sealed tube. The tube in the left beaker is labeled T equals 0. It is full of a colorless gas which is connected to a zoom-in view of the particles in the tube by a downward-facing arrow. This particle view shows 7 particles, each composed of 2 connected blue spheres. Each blue sphere is connected to 2 red spheres. This type of particle is labeled N subscript 2 O subscript 4. The tube in the middle beaker is labeled pre-equilibrium. It is full of a light brown gas which is connected to a zoom-in view of the particles in the tube by a downward-facing arrow. This particle view shows 9 particles, 5 of which are composed of 2 connected blue spheres. Each blue sphere is connected to 2 red spheres. This type of particle is labeled N subscript 2 O subscript 4. The remaining 4 are composed of 2 red spheres connected to a blue sphere. This type of particle is labeled N O subscript 2. The tube in the right beaker is labeled at equilibrium. It is full of a brown gas which is connected to a zoom-in view of the particles in the tube by a downward-facing arrow. This particle view shows 11 particles, 3 of which are composed of 2 connected blue spheres. Each blue sphere is connected to 2 red spheres. The remaining 8 are composed of 2 red spheres connected to a blue sphere. In part B, in the middle of the image, is one graph. This graph has a y-axis labeled concentration and an x-axis labeled time. A red line labeled NO subscript 2 begins in the bottom left corner of the graph at a point labeled 0 and rises near the highest point on the y-axis before it levels off and becomes horizontal. A blue line labeled N subscript 2 O subscript 4 begins near the highest point on the y-axis and drops below the midpoint of the y-axis before leveling off. In part C, at the bottom of the image is another graph. This graph has a y-axis labeled rate and an x-axis labeled time. A red line labeled K subscript F, N subscript 2 O subscript 4 begins in the bottom left corner of the graph at a point labeled 0 and rises near the middle of the y-axis before it levels off and becomes horizontal. A blue line labeled K subscript F, N O subscript 2 superscript 2 begins near the highest point on the y-axis and drops to the same point on the y-axis as the red line before leveling off. The point where both lines become horizontal is labeled equilibrium achieved. Figure 13.2. A sealed tube containing colorless N2O4 darkens as it decomposes to yield brown NO2. B changes in concentration over time as the decomposition reaction achieves equilibrium. C. At equilibrium, the forward and reverse reaction rates are equal. For this elementary process, rate laws for the forward and reverse reactions may be derived directly from the reaction stoichiometry. R at T, E, letter 1D453, equals letter 1D458, letter 1D453 and 204. R at T, E, letter 1D45F, equals letter 1D458, letter 1D45F, no, 22. As the reaction begins, T equals 0. The concentration of the N2O4 reactant is finite, and that of the NO2 product is 0. So the forward reaction proceeds at a finite rate, while the reverse reaction rate is 0. As time passes, N2O4 is consumed and its concentration falls, while NO2 is produced and its concentration increases. Figure 13. 2b. The decreasing concentration of the reactant slows the forward reaction rate, and the increasing product concentration speeds the reverse reaction rate. Figure 13. 2c. This process continues until the forward and reverse reaction rates become equal, at which time the reaction has reached equilibrium, as characterized by constant concentrations of its reactants and products, shaded areas of Figure 13. 2b and Figure 13. 2c. It's important to emphasize that chemical equilibria are dynamic. A reaction at equilibrium has not stopped, but is proceeding in the forward and reverse directions at the same rate. This dynamic nature is essential to understanding equilibrium behavior as discussed in this and subsequent chapters of the text. Two people are shown throwing juggling pins back and forth to one another. Figure 13. 3. A two-person juggling act illustrates the dynamic aspect of chemical equilibria. Each person is throwing and catching clubs at the same rate, and each holds a approximately constant number of clubs. Physical changes, such as phase transitions, are also reversible and may establish equilibria. This concept was introduced in another chapter of this text through discussion of the vapor pressure of a condensed phase, liquid or solid. As one example, consider the vaporization of bromine. Br2, letter 1D459, Br2, letter 1D454. When liquid bromine is added to an otherwise empty container, and the container is sealed, the forward process depicted above, vaporization, will commence and continue at a roughly constant rate as long as the exposed surface area of the liquid and its temperature remain constant. As increasing amounts of gaseous bromine are produced, the rate of the reverse process, condensation, will increase until it equals the rate of vaporization and equilibrium is established. A photograph showing this phase transition equilibrium is provided in Figure 13. For a glass container is shown that is filled with an orange-brown gas and a small amount of dark orange liquid. Figure 13. For a sealed tube containing an equilibrium mixture of liquid and gaseous bromine. Credit, http, images of elements, com bromine, php. Learning objectives. By the end of this section, you will be able to derive reaction quotients from chemical equations representing homogeneous and heterogeneous reactions, calculate values of reaction quotients and equilibrium constants. Using concentrations and pressures, relate the magnitude of an equilibrium constant to properties of the chemical system. The status of a reversible reaction is conveniently assessed by evaluating its reaction quotient, Q. For a reversible reaction described by letter 1D45A, a plus letter 1D45BB, plus letter 1D465C, plus letter 1D466D. The reaction quotient is derived directly from the stoichiometry of the balanced equation, as letter 1D444 letter 1D450 equals C letter 1D465D letter 1D466A letter 1D45AB letter 1D45B, where the subscript C denotes the use of molar concentrations in the expression. If the reactants and products are gaseous, a reaction quotient may be similarly derived using partial pressures. Letter 1D444 letter 1D45D equals letter 1D443 C letter 1D465, letter 1D443, D letter 1D466, letter 1D443. A letter 1D45A, letter 1D443B, letter 1D45B. Note that the reaction quotient equations above are a simplification of more rigorous expressions that use relative values for concentrations and pressures rather than absolute values. These relative concentration and pressure values are dimensionless. They have no units. Consequently, so are the reaction quotients. For purposes of this introductory text, it will suffice to use the simplified equation and to disregard units when computing Q. In most cases, this will introduce only modest errors in calculations involving reaction quotients. Example 13. One writing reaction quotient expressions. Write the concentration-based reaction quotient expression for each of the following reactions. A3O2 letter 1D454 letter 1D454. B. N2 letter 1D454 plus 3H2 letter 1D454 2NH3 letter 1D454. C. 4NH3 letter 1D454 plus 7O2 letter 1D454 4NO2 letter 1D454 plus 6H2 letter 1D454. Solution AOOB. Letter 1D444 letter 1D450 equals NH 32N2H23. C. Letter 1D444 letter 1D450 equals No 24H2O6NH 34027. Check your learning. Write the concentration-based reaction quotient expression for each of the following reactions. A2 SO2 letter 1D454 plus O2 letter 1D4542 SO3 letter 1D454. B C4H8 letter 1D454 2 CH4 letter 1D454 C2C4H10 letter 1D454 plus 13O2 letter 1D4548 Co2 letter 1D454 plus 10H2 letter 1D454 answer. A letter 1D444 letter 1D450 equals so 32 2202. B letter 1D444 letter 1D450 equals seat H42C 4H8. C letter 1D444 letter 1D450 equals code 28H2O10C 4H1020 4 graphs are shown and labeled A, B, C, and D. All 4 graphs have a vertical dotted line running through the middle labeled equilibrium is reached. The y-axis on graph A is labeled concentration and the x-axis is labeled time. 3 curves are plotted on graph A. The first is labeled SO subscript 2. This line starts high on the y-axis, ends midway down the y-axis, has a steep initial slope and a more gradual slope as it approaches the far right on the x-axis. The second curve on this graph is labeled O subscript 2. This line mimics the first except that it starts and ends about 50% lower on the y-axis. The third curve is the inverse of the first in shape and is labeled SO subscript 3. The y-axis on graph B is labeled concentration and the x-axis is labeled time. 3 curves are plotted on graph B. The first is labeled SO subscript 2. This line starts low on the y-axis, ends midway up the y-axis, has a steep initial slope and a more gradual slope as it approaches the far right on the x-axis. The second curve on this graph is labeled O subscript 2. This line mimics the first except that it ends about 50% lower on the y-axis. The third curve is the inverse of the first in shape and is labeled SO subscript 3. The y-axis on graph C is labeled reaction quotient and the x-axis is labeled time. A single curve is plotted on graph C. This curve begins at the bottom of the y-axis and rises steeply up near the top of the y-axis, then levels off into a horizontal line. The top point of this line is labeled K. The y-axis on graph D is labeled reaction quotient and the x-axis is labeled time. A single curve is plotted on graph D. This curve begins near the edge of the top of the y-axis and falls steeply toward the x-axis, then levels off into a horizontal line. The bottom point of this line is labeled K. Figure 13. 5 changes in concentrations and QC for a chemical equilibrium, achieved beginning with A, a mixture of reactants only, and B, products only. The numerical value of Q varies as a reaction proceeds towards equilibrium. Therefore, it can serve as a useful indicator of the reaction status. To illustrate this point, consider the oxidation of sulfur dioxide, 2SO2, letter 1D454, plus O2, letter 1D454 2SO3, letter 1D454. 2 different experimental scenarios are depicted in Figure 13. 5. One in which this reaction is initiated with a mixture of reactants only, SO2 and O2, and another that begins with only product, SO3. For the reaction that begins with a mixture of reactants only, Q is initially equal to 0. So as the reaction proceeds toward equilibrium in the forward direction, reactant concentrations decrease, as does the denominator of QC. Product concentration increases, as does the numerator of QC, and the reaction quotient consequently increases. When equilibrium is achieved, the concentrations of reactants and product remain constant, as does the value of QC. If the reaction begins with only product present, the value of QC is initially undefined, immeasurably large or infinite. Letter 1D444 letter 1D450 equals so 32 220 2 equals so 320 right infinity in this case. The reaction proceeds toward equilibrium in the reverse direction. The product concentration and the numerator of QC decrease with time. The reactant concentrations and the denominator of QC increase, and the reaction quotient consequently decreases until it becomes constant at equilibrium. The constant value of Q exhibited by a system at equilibrium is called the equilibrium constant, K. Letter 1D43E identical to letter 1D444, a T equilibrium comparison of the data plots in Figure 13. 5 shows that both experimental scenarios resulted in the same value for the equilibrium constant. This is a general observation for all equilibrium systems, known as the law of mass action. At a given temperature, the reaction quotient for a system at equilibrium is constant. Example 13. 2. Evaluating a reaction quotient gaseous nitrogen dioxide forms dinitrogen tetroxide according to this equation. 2 No 2, letter 1D454, N2O4, letter 1D454, when 0. 10 mol NO2 is added to a 10L flask at 25 degrees C. The concentration changes so that at equilibrium, NO2 equals 0. 16 m and N2O4 equals 0. 42 m. A. What is the value of the reaction quotient before any reaction occurs? B. What is the value of the equilibrium constant for the reaction? Solution as for all equilibrium calculations in this text. Use the simplified equations for Q and K and disregard any concentration or pressure units, as noted previously in this section. A. Before any product is formed, NO2 equals 0, 10 mol 1, 0 L equals 0, 10 m, and N2O4 equals m. Thus, letter 1D444, letter 1D450 equals N2O, 4 NO22 equals 0, 0. 102 equals 0, B. At equilibrium, letter 1D43, letter 1D450 equals letter 1D444, letter 1D450 equals N2O, 4 NO22 equals 0. 420. 6 times 102. The equilibrium constant is 6 times 102. Check your learning for the reaction 2, so 2, letter 1D454 plus O2, letter 1D4542, so 3, letter 1D454. The concentrations at equilibrium are so 2 equals 0. 90 m, O2 equals 0. 35 m and so 3 equals 1 m. What is the value of the equilibrium constant Kc? Answer: Kc equals 4. 3. By its definition, the magnitude of an equilibrium constant explicitly reflects the composition of a reaction mixture at equilibrium, and it may be interpreted with regard to the extent of the forward reaction. A reaction exhibiting a large K will reach equilibrium when most of the reactant has been converted to product, whereas a small K indicates the reaction achieves equilibrium after very little reactant has been converted. It's important to keep in mind that the magnitude of K does not indicate how rapidly or slowly equilibrium will be reached. Some equilibria are established so quickly as to be nearly instantaneous, and others so slowly that no perceptible change is observed over the course of days, years, or longer. The equilibrium constant for a reaction can be used to predict the behavior of mixtures containing its reactants and/or products. As demonstrated by the sulfur dioxide oxidation process described above, a chemical reaction will proceed in whatever direction is necessary to achieve equilibrium. Comparing Q to K for an equilibrium system of interest allows prediction of what reaction, forward or reverse, if any, will occur. To further illustrate this important point, consider the reversible reaction shown below. CoHO2, letter 1D454 plus H2, letter 1D454, letter 1D43, letter 1D450 equals 0. 640 T equals 800 degrees C. The bar charts in Figure 13. 6. Represent changes in reactant and product concentrations for 3 different reaction mixtures. The reaction quotients for mixtures 1 and 3 are initially lesser than the reaction's equilibrium constant, so each of these mixtures will experience a net forward reaction to achieve equilibrium. The reaction quotient for mixture 2 is initially greater than the equilibrium constant, so this mixture will proceed in the reverse direction until equilibrium is established. 2 sets of bar graphs are shown. The left is labeled before reaction and the right is labeled at equilibrium. Both graphs have y-axes labeled concentration M and 3 bars on the x-axis labeled mixture 1, mixture 2, and mixture 3. The y-axis has a scale beginning at 0 and ending at 010 with measurement increments of 0, 2. The bars on the graphs are color-coded and a key is provided with a legend. Red is labeled CO, blue is labeled H subscript 2O, green is labeled CO subscript 2, and yellow is labeled H subscript 2. The graph on the left shows the red bar for mixture 1 just above 0, 2 labeled 0243, and the blue bar near 05 labeled 0243. For mixture 2, the green bar is near 05 labeled 0468, and the yellow bar is near 09 labeled 0468. For mixture 3, the red bar is near 01 labeled 0330. The blue bar is slightly above that, labeled 0190, with green and yellow topping it off at 02. Green is labeled 0175, and yellow is labeled 0160. On the right graph, the bar for mixture 1 shows the red bar slightly above 01, labeled 0135. The blue bar stacked on it rising slightly above 02, labeled 0135. The green rising near 04, labeled 0108, and the yellow bar reaching near 05, labeled 0108. A label above this bar reads Q equals 640. The bar for mixture 2 shows the red bar slightly above 02, labeled 0260. The blue bar stacked on it rising near 05, labeled 0260. The green rising near 07, labeled 0208, and the yellow bar reaching near 010, labeled 0208. A label above this bar reads Q equals 640. The bar for mixture 3 shows the red bar near 01, labeled 0231. The blue bar stacked on it rising slightly above 01, labeled 0909. The green rising near 02, labeled 0115, and the yellow bar reaching 02, labeled 0117. A label above this bar reads Q equals 640, figure 13. 6 compositions of 3 mixtures before QC not equal to KC. And after QC equals KC, equilibrium is established for the reaction CO, letter 1D454, plus H2O, letter 1D454, CO2, letter 1D454, plus H2, letter 1D454. Example 13. 3. Predicting the direction of reaction given here are the starting concentrations of reactants and products for 3 experiments involving this reaction. CoHO CO2, letter 1D454 plus H2, letter 1D454, letter 1D43, letter 1D450 equals 0. 64. Determine in which direction the reaction proceeds as it goes to equilibrium in each of the 3 experiments shown. Reactants products experiment 1, experiment 2, experiment 3 CoI0, 20 M0, 11 M0, 94 MH2OI0, 20 M0, 11 M0, 25 M CO2I0, 40 M0, 37 M0, 15 MH2I0, 40 M0, 46 M0, 76 M. Solution experiment 1. Letter 1D444, letter 1D450 equals CO2H2 CoH2O equals 0, 0, 0, 4, 0, 0, 0, 0, 4, 0, 0, 0, 20, 0, 40, QCKC 0, 40, 0, 64. The reaction will proceed in the forward direction. Experiment 2. Letter 1D444, letter 1D450 equals CO2H2 CoH2O equals 0, 037, 0, 046, 0, 011, 0, 0011 equals 1. 4 times 102 QCKC, 140, 0. 64. The reaction will proceed in the reverse direction. Experiment 3. Letter 1D444 letter 1D450 equals code 2H2 co H to O equals 0. 00150, 0076, 00940, 0025 equals 0. 48 QCKC 0480. 64. The reaction will proceed in the forward direction. Check your learning, calculate the reaction quotient, and determine the direction in which each of the following reactions will proceed to reach equilibrium. A 1. L flask containing 500 mol of No G, 155 mol of Cl2G, and 500 mol of NaCl. 2 No letter 1D454 plus Cl2 letter 1D4542 NaCl letter 1D454 letter 1D43 letter 1D450 equals 4. 6 times 104B, a 5. 0 L flask containing 17 G of NH3, 14 G of N2, and 12 G of H2. N2, letter 1D454, plus 3 H2, letter 1D4542 NH3, letter 1D454, letter 1D43, letter 1D450 equals 0. 60 C. A 20 L flask containing 230 G of SO3G. 2 SO3, letter 1D4542 SO2, letter 1D454, plus O2, letter 1D454, letter 1D43, letter 1D450 equals 0. 230 Answer. A. QC equals 645 times 103 forward. B. QC equals 023 reverse. C. QC equals 0 forward. Homogeneous equilibria. A homogeneous equilibrium is one in which all reactants and products, and any catalysts, if applicable, are present in the same phase. By this definition, homogeneous equilibria take place in solutions. These solutions are most commonly either liquid or gaseous phases, as shown by the examples below. Seat H2, letter 1D44, letter 1D45E, plus 2Br2, letter 1D44, letter 1D45E. 2, letter 1D44, letter 1D45E plus I minus, letter 1D44, letter 1D45E HF, letter 1D44, letter 1D45E, plus H2, letter 1D459 and H3, letter 1D44, letter 1D45E plus H2, letter 1D459 C2H2. Br4, letter 1D44, letter 1D45E. 3 minus, letter 1D44, letter 1D45E H3O plus, letter 1D44, letter 1D45E plus F minus, letter 1D44, letter 1D45E NH, 4 plus, letter 1D44, letter 1D45E, plus O minus, letter 1D44, letter 1D45E, letter 1D43, letter 1D450, letter 1D43, letter 1D450, letter 1D43, letter 2H to Br4 C to H 2 Br2 to A 3 minus I 2I minus H3 O plus F minus HF NH 4 plus O minus NH3. These examples all involve aqueous solutions, those in which water functions as the solvent. In the last two examples, water also functions as a reactant, but its concentration is not included in the reaction quotient. The reason for this omission is related to the more rigorous form of the Q or K expression mentioned previously in this chapter, in which relative concentrations for liquids and solids are equal to 1 and needn't be included. Consequently, reaction quotients include concentration or pressure terms only for gaseous and solute species. The equilibria below all involve gas phase solutions. Seat H6. Letter 1D454302, letter 1D454N2, letter 1D454, plus 3H2, letter 1D454C3H8, letter 1D454, plus 5O2, letter 1D454, seat H4, letter 1D454, plus H2, letter 1D454203, letter 1D4542 and H3, letter 1D4543 Co2, letter 1D454 plus 4H2, O letter 1D454. Letter 1D43, letter 1D450, letter 1D43, letter 1D450, letter 1D43, letter 1D450, letter 1D43, letter 1D450, equals seat H4H, 2C2H, 6O320, 23NH, 32N2H, 23 Co, 23H4C3, H8O25 for gas phase solutions. The equilibrium constant may be expressed in terms of either the molar concentrations, Kc, or partial pressures, Kp, of the reactants and products. A relation between these two K values may be simply derived from the ideal gas equation and the definition of molarity. Letter 1D443, letter 1D449 equals letter 1D45B, letter 1D445, letter 1D447, letter 1D443 equals letter 1D45B, letter 1D449, letter 1D445, letter 1D447 equals letter 1D440, letter 1D445, letter 1D447, where P is partial pressure, V is volume, N is molar amount, R is the gas constant, T is temperature, and M is molar concentration. For the gas phase reaction, letter 1D440, a plus letter 1D44FB, letter 1D450C, plus letter 1D451D. Letter 1D43, letter 1D443 equals letter 1D443, letter 1D436, letter 1D450. Letter 1D443, letter 1D437, letter 1D451, letter 1D443, letter 1D434, letter 1D448, letter 1D443, letter 1D435, letter 1D44F equals C times letter 1D445, letter 1D447, letter 1D450, D times letter 1D445, letter 1D447, letter 1D451, A times letter 1D445, letter 1D447, letter 1D440, B times letter 1D445, letter 1D447, letter 1D44F equals C letter 1D450, D letter 1D451, A letter 1D44E, B letter 1D44F times letter 1D445, letter 1D447, letter 1D450, plus letter 1D451, letter 1D445, letter 1D447, letter 1D440, plus letter 1D44F equals letter 1D43, letter 1D450, letter 1D445, letter 1D447, letter 1D450, plus letter 1D451 minus letter 1D440 plus letter 1D44F equals letter 1D43, letter 1D450, letter 1D445, letter 1D447, delta letter 1D45B, and so. The relationship between Kc and Kp is letter 1D43, letter 1D443 equals letter 1D43, letter 1D450, letter 1D445, letter 1D447, delta letter 1D45B, where delta is the difference in the molar amounts of product and reactant gases. In this case, delta letter 1D45B equals letter 1D450 plus letter 1D451 minus letter 1D440 plus letter 1D44F. Example 13. For calculation of Kp, write the equations relating Kc to Kp for each of the following reactions. A seat H6, letter 1D454 seat H4, letter 1D454 plus H2 letter 1D454, B co letter 1D454, plus H2 letter 1D454 co 2 letter 1D454 plus H2 letter 1D454, C, N2 letter 1D454 plus 3H2 letter 1D454 2 and H3 letter 1D454, D Kc is equal to 0. 28 for the following reaction at 900 C. CS2 letter 1D454 plus 4H2 letter 1D454 CH4 letter 1D454 plus 2H2S letter 1D454. What is Kp at this temperature? Solution A. Delta equals 2 minus 1 equals 1 Kp equals Kc. RT delta equals Kc RT. 1 equals Kc RT. B. Delta equals 2 minus 2 equals 0 Kp equals Kc RT. Delta equals Kc RT. 0 equals Kc C. Delta equals 2 minus 1 plus 3 equals minus 2 Kp equals Kc RT. Delta equals Kc RT minus 2 equals letter 1D43, letter 1D450, letter 1D445, letter 1D447 2, D, Kp equals Kc, RT delta equals 0. 28, 0, 0821, 1173, minus 2 equals 3 times 10 minus 5. Check your learning. Write the equations relating Kc to Kp for each of the following reactions. A2 so 2 letter 1D454. plus O2 letter 1D4542 SO3 letter 1D454. B into O4 letter 1D4542 No 2 letter 1D454. C C3H8 letter 1D454 plus 5O2 letter 1D4543 CO2 letter 1D454 plus 4H2 letter 1D454. D at 227 degrees C. The following reaction has Kc equals 0. 952. CH3O letter 1D454, Co letter 1D454, plus 2H2 letter 1D454. What would be the value of Kp at this temperature? Answer. A. Kp equals KCRT minus 1. B. Kp equals KCRT. C. Kp equals KCRT. D. 160 or 1. 6 times 102 heterogeneous equilibria. A heterogeneous equilibrium involves reactants and products in 2 or more different phases, as illustrated by the following examples. PbCl2, letter 1D460. Ka O letter 1D460 plus Co2 letter 1D454 C letter 1D460 plus 2s letter 1D454 Br2 letter 1D459 Pb2 plus letter 1D44 letter 1D45 plus 2Cl minus letter 1D44 letter 1D45 Kako 3 letter 1D460 CS2 letter 1D454 Br2 letter 1D454 letter 1D43 letter. Again, note that concentration terms are only included for gaseous and solute species, as discussed previously. 2 of the above examples include terms for gaseous species only in their equilibrium constants, and so Kp expressions may also be written. Ka-O letter 1D460 plus Co2 letter 1D454C letter 1D460 plus 2's letter 1D454 Kako3 letter 1D460 CS2 letter 1D454 letter 1D43 letter 1D443 letter 1D43 letter 1D443 equals 1 letter 1D443 CO letter 1D443 CS 2 letter 1D443 S2. Coupled equilibria, the equilibrium systems discussed so far, have all been relatively simple, involving just single reversible reactions. Many systems, however, involve 2 or more coupled equilibrium reactions, those which have in common one or more reactant or product species. Since the law of mass action allows for a straightforward derivation of equilibrium constant expressions from balanced chemical equations, the K value for a system involving coupled equilibria can be related to the K values of the individual reactions. 3 basic manipulations are involved in this approach, as described below. 1. Changing the direction of a chemical equation essentially swaps the identities of reactants and products, and so the equilibrium constant for the reversed equation is simply the reciprocal of that for the forward equation. A BKC equals BAB AC equals AB KC equals 1 KC2. Changing the stoichiometric coefficients in an equation by some factor x results in an exponential change in the equilibrium constant by that same factor. A BKC equals BAX, a XBKC equals BXAX KC equals KCX3. Adding 2 or more equilibrium equations together yields an overall equation, whose equilibrium constant is the mathematical product of the individual reactions' K values. A BKC1 equals BAB, CKC2 equals CB. The net reaction for these coupled equilibria is obtained by summing the 2 equilibrium equations and canceling any redundancies. A plus BB plus Ka plus BB plus Ka CKC equals CA. Comparing the equilibrium constant for the net reaction to those for the 2 coupled equilibrium reactions reveals the following relationship. Kc1 Kc2 equals Ba times Cb equals BCa B equals Ca equals Kc Kc equals Kc1 Kc2, example 13. 5 demonstrates the use of this strategy in describing coupled equilibrium processes. Example 13. 5 equilibrium constants for coupled reactions, a mixture containing nitrogen, hydrogen, and iodine, establish the following equilibrium at 400 degrees C. 2NH3, letter 1D454, plus 3A2, letter 1D454N2, letter 1 D454, plus 6 high, letter 1 D454. Use the information below to calculate Kc for this reaction. N2, letter 1 D454, plus 3H2, letter 1 D4542 NH3, letter 1 D454H2, letter 1 D454 plus I2, letter 1 D4542, high letter 1 D454 Kc1 equals 0. 50 at 400 degrees C Kc2 equals 50 at 400 degrees C solution. The equilibrium equation of interest and its K value may be derived from the equations for the two coupled reactions as follows. Reverse the first coupled reaction equation. 2NH3, letter 1 D454 N2, letter 1 D454, plus 3H2, letter 1 D454. Kc1 equals 1, Kc1 equals 10. 50 equals 2. Multiply the second coupled reaction by 3. 3H2, letter 1 D454, plus 3I2, letter 1 D454, 6 high, letter 1 D454. Kc2 equals K3C2 equals 503 equals 1. 2 times 105 finally. Add the two revised equations. 2NH3, letter 1 D454, plus 3H2, letter 1 D454, plus 3I2, letter 1 D454, letter 1 D4412, letter 1 D454, plus 3H2, letter 1 D454, plus 6 high, letter 1 D4542 NH3, letter 1 D454, plus 3I2, letter 1 D454, letter 1 D4412, letter 1 D454, plus 6 high, letter 1 D454, Kc equals Kc1, Kc2 equals 2. 0, 1. 2 times 105 equals 2. 5 times 105. Check your learning. Use the provided information to calculate Kc for the following reaction at 550 degrees C. H2, letter 1 D454, plus CO2, letter 1 D454 CO, letter 1 D454 plus H2, letter 1 D454 CO, O, letter 1 D460 plus CO, letter 1 D454 CO, letter 1 D460 plus CO2, letter 1 D454 CO, O, letter 1 D460 plus H2, letter 1 D454 CO, letter 1 D460 plus H2, letter 1 D442, letter 1 D454 Kc equals Kc1 equals 490, Kc1 equals 67. Answer. Kc equals 014. Learning objectives. By the end of this section, you will be able to describe the ways in which an equilibrium system can be stressed, predict the response of a stressed equilibrium using Le Chatelier's principle. A system at equilibrium is in a state of dynamic balance, with forward and reverse reactions taking place at equal rates. If an equilibrium system is subjected to a change in conditions that affects these reaction rates differently, a stress, then the rates are no longer equal and the system is not at equilibrium. The system will subsequently experience a net reaction in the direction of greater rate, a shift that will re-establish the equilibrium. This phenomenon is summarized by Le Chatelier's principle. If an equilibrium system is stressed, the system will experience a shift in response to the stress that re-establishes equilibrium. Reaction rates are affected primarily by concentrations, as described by the reactions rate law, and temperature, as described by the Arrhenius equation. Consequently, changes in concentration and temperature are the two stresses that can shift an equilibrium. Effect of a change in concentration. If an equilibrium system is subjected to a change in the concentration of a reactant or product species, the rate of either the forward or the reverse reaction will change. As an example, consider the equilibrium reaction. H2, letter 1 D454, plus I2, letter 1 D454 2 high, letter 1 D454, letter 1 D43, letter 1 D450 equals 50. At degree C, the rate laws for the forward and reverse reactions are letter 1 D453, letter 1 D45C, letter 1 D45F, letter 1 D464, letter 1 D44, letter 1 D45F, H2, letter 1 D454 plus I2, letter 1 D454. Right arrow 2 high, letter 1 D454, letter 1 D45F, letter 1 D452, letter 1 D463, letter 1 D452, letter 1 D45F, letter 1 D460 high, letter 1 D454. Right arrow H2, letter 1 D454 plus I2 letter 1 D454. R a T E letter 1 D453 equals letter 1 D458 letter 1 D453 H 2 letter 1 D45A 2 letter 1 D45B R a T E letter 1 D45F equals letter 1 D458 letter 1 D45F high letter 1 D465. When this system is at equilibrium, the forward and reverse reaction rates are equal. R a T E letter 1 D453 equals R a T E letter 1 D45F. If the system is stressed by adding reactant, either H2 or I2, the resulting increase in concentration causes the rate of the forward reaction to increase, exceeding that of the reverse reaction. R a T E letter 1 D453, R a T E letter 1 D45F. The system will experience a temporary net reaction in the forward direction to re-establish equilibrium. The equilibrium will shift right. This same shift will result if some product HI is removed from the system, which decreases the rate of the reverse reaction, again resulting in the same imbalance in rates. The same logic can be used to explain the left shift that results from either removing reactant or adding product to an equilibrium system. These stresses both result in an increased rate for the reverse reaction. R a T E letter 1 D453, R a T E letter 1 D45F, and a temporary net reaction in the reverse direction to re-establish equilibrium. As an alternative to this kinetic interpretation, the effect of changes in concentration on equilibria can be rationalized in terms of reaction quotients. When the system is at equilibrium, letter 1 D444 letter 1 D450 equals high 2H, 2I, 2 equals letter 1 D43 letter 1 D450. If reactant is added, increasing the denominator of the reaction quotient, or product is removed, decreasing the numerator, then QC, KC and the equilibrium will shift right. Note that the three different ways of inducing this stress result in three different changes in the composition of the equilibrium mixture. If H2 is added, the right shift will consume I2 and produce HI as equilibrium is re-established, yielding a mixture with a greater concentrations of H2 and HI and a lesser concentration of I2 than was present before. If I2 is added, the new equilibrium mixture will have greater concentrations of I2 and HI and a lesser concentration of H2. Finally, if HI is removed, the concentrations of all three species will be lower when equilibrium is re-established. Despite these differences in composition, the value of the equilibrium constant will be the same after the stress as it was before, per the law of mass action. The same logic may be applied for stresses involving removing reactants or adding product, in which case QC, KC and the equilibrium will shift left. For gas phase equilibria such as this one, some additional perspectives on changing the concentrations of reactants and products are worthy of mention. The partial pressure P of an ideal gas is proportional to its molar concentration M. Letter 1 D440 equals letter 1 D45B, letter 1 D449 equals letter 1 D443, letter 1 D445, letter 1 D447. And so changes in the partial pressures of any reactant or product are essentially changes in concentrations, and thus yield the same effects on equilibria. Aside from adding or removing reactant or product, the pressures, concentrations of species in a gas phase equilibrium can also be changed by changing the volume occupied by the system. Since all species of a gas phase equilibrium occupy the same volume, a given change in volume will cause the same change in concentration for both reactants and products. In order to discern what shift, if any, this type of stress will induce, the stoichiometry of the reaction must be considered. At equilibrium, the reaction H2G plus I2G2 high G is described by the reaction quotient. Letter 1 D444, letter 1 D443 equals letter 1 D443 H high to pH to letter 1 D443, letter 1 D43C. 2 equals letter 1 D43, letter 1 D443. If the volume occupied by an equilibrium mixture of these species is decreased by a factor of 3. The partial pressures of all three species will be increased by a factor of 3. And so, changing the volume of this gas phase equilibrium mixture does not result in a shift of the equilibrium. A similar treatment of a different system, 2No2G, 2No G plus O2G, however, yields a different result. Letter 1D444 letter 1D443 equals letter 1D443 NO to POTA. Letter 1D443 NO, 22 letter 1D444 letter 1D443 equals 3 letter 1D443 NO, 23 letter 1D443 O23 letter 1D443 NO, 22 equals 9 letter 1D443 NO, 23 letter 1D443 O29 letter 1D443 NO, 22 equals 27 letter 1D443 and O. Letter 1D443, O29 letter 1D443 and O. 22 equals 3 letter 1D443 and O to pot letter 1D443 and O. 22 equals 3 letter 1D444 letter 1D443. Letter 1D43 letter 1D443 letter 1D444 letter 1D443 equals 3 letter 1D444 letter 1D443. Letter 1D43 letter 1D443. In this case, the change in volume results in a reaction quotient greater than the equilibrium constant, and so the equilibrium will shift left. These results illustrate the relationship between the stoichiometry of a gas phase equilibrium and the effect of a volume-induced pressure, concentration change. If the total molar amounts of reactants and products are equal, as in the first example, a change in volume does not shift the equilibrium. If the molar amounts of reactants and products are different, a change in volume will shift the equilibrium in a direction that better accommodates the volume change. In the second example, 2 moles of reactant, NO2, yield 3 moles of product, 2No plus O2. And so decreasing the system volume causes the equilibrium to shift left since the reverse reaction produces less gas, 2 mol, than the forward reaction, 3 mol. Conversely, increasing the volume of this equilibrium system would result in a shift towards products. Link to learning. Check out this link to see a dramatic visual demonstration of how equilibrium changes with pressure changes. Chemistry in everyday life. Equilibrium and soft drinks. The connection between chemistry and carbonated soft drinks goes back to 1767, when Joseph Priestley, 1730–1804, developed a method of infusing water with carbon dioxide to make carbonated water. Priestley's approach involved production of carbon dioxide by reacting oil of vitriol sulfuric acid with chalk calcium carbonate. The carbon dioxide was then dissolved in water, reacting to produce hydrogen carbonate, a weak acid that subsequently ionized to yield bicarbonate and hydrogen ions. Dissolution CO2, letter 1D454, CO2, letter 1D44, letter 1D45E. Hydrolysis CO2, letter 1D44, letter 1D45E plus H2O, letter 1D459 H2CO3, letter 1D44, letter 1D45E ionization H2CO3, letter 1D44, letter 1D45E, HCO3 minus, letter 1D44, letter 1D45E plus, H plus letter 1D44, letter 1D45E. These same equilibrium reactions are the basis of today's soft drink carbonation process. Beverages are exposed to a high pressure of gaseous carbon dioxide during the process to shift the first equilibrium above to the right, resulting in desirably high concentrations of dissolved carbon dioxide, and per similar shifts in the other two equilibria, its hydrolysis and ionization products. A bottle or can is then nearly filled with the carbonated beverage, leaving a relatively small volume of air in the container above the beverage surface, the headspace, before it is sealed. The pressure of carbon dioxide in the container headspace is very low immediately after sealing, but it rises as the dissolution equilibrium is re-established by shifting to the left. Since the volume of the beverage is significantly greater than the volume of the headspace, only a relatively small amount of dissolved carbon dioxide is lost to the headspace. When a carbonated beverage container is opened, A hissing sound is heard as pressurized CO2 escapes from the headspace. This causes the dissolution equilibrium to shift left, resulting in a decrease in the concentration of dissolved CO2 and subsequent left shifts of the hydrolysis and ionization equilibria. Fortunately for the consumer, the dissolution equilibrium is usually re-established slowly, and so the beverage may be enjoyed while its dissolved carbon dioxide concentration remains palatably high. Once the equilibria are re-established, the CO2 AC concentration will be significantly lowered, and the beverage acquires a characteristic taste referred to as flat. A bottle of soda sitting on the ground is shown with a large amount of fizz-filled liquid spewing out of the top. Figure 13. 7. Opening a soft drink bottle lowers the CO2 pressure above the beverage, shifting the dissolution equilibrium and releasing dissolved CO2 from the beverage. Credit, modification of work by D. Coetzee/Flicker. Effect of a change in temperature. Consistent with the law of mass action, an equilibrium stressed by a change in concentration will shift to re-establish equilibrium without any change in the value of the equilibrium constant, K, when an equilibrium shifts in response to a temperature change. However, it is re-established with a different relative composition that exhibits a different value for the equilibrium constant. To understand this phenomenon, consider the elementary reaction. B. Since this is an elementary reaction, the rate's laws for the forward and reverse may be derived directly from the balanced equation stoichiometry. R a T E letter 1 D453 equals letter 1 D458 letter 1 D453 AR. A T E letter 1 D45F equals letter 1 D458 letter 1 D45FB. When the system is at equilibrium, R a T E letter 1 D45F equals R a T E letter 1 D453. Substituting the rate laws into this equality and rearranging gives letter 1 D458 letter 1 D453A equals letter 1 D458 letter 1 D45FB letter 1 D435 letter 1 D434 equals letter 1 D458 letter 1 D453 letter 1 D458 letter 1 D45F equals letter 1 D43 letter 1 D450. The equilibrium constant is seen to be a mathematical function of the rate constants for the forward and reverse reactions. Since the rate constants vary with temperature as described by the Arrhenius equation, it stands to reason that the equilibrium constant will likewise vary with temperature, assuming the rate constants are affected to different extents by the temperature change. For more complex reactions involving multi-step reaction mechanisms, a similar but more complex mathematical relation exists between the equilibrium constant and the rate constants of the steps in the mechanism. Regardless of how complex the reaction may be, the temperature dependence of its equilibrium constant persists. Predicting the shift an equilibrium will experience in response to a change in temperature is most conveniently accomplished by considering the enthalpy change of the reaction. For example, the decomposition of dinitrogen tetroxide is an endothermic, heat-consuming process. N2O4, letter 1 D454, 2 No 2, letter 1 D454 delta letter 1 D43B equals plus 57. 20 kJ. For purposes of applying Le Chatelier's principle, heat Q may be viewed as a reactant. Heat plus N2O4, letter 1 D454, 2 No 2, letter 1 D454. Raising the temperature of the system is akin to increasing the amount of a reactant, and so the equilibrium will shift to the right. Lowering the system temperature will likewise cause the equilibrium to shift left. For exothermic processes, heat is viewed as a product of the reaction, and so the opposite temperature dependence is observed. Effect of a catalyst. The kinetics chapter of this text identifies a catalyst as a substance that enables a reaction to proceed via a different mechanism with an accelerated rate. The catalyzed reaction mechanism involves a lower energy transition state than the uncatalyzed reaction, resulting in a lower activation energy, E, and a correspondingly greater rate constant. To discern the effect of catalysis on an equilibrium system, consider the reaction diagram for a simple one-step, elementary, reaction shown in Figure 13.8. The lowered transition state energy of the catalyzed reaction results in lowered activation energies for both the forward and the reverse reactions. Consequently, both forward and reverse reactions are accelerated, and equilibrium is achieved more quickly but without a change in the equilibrium constant. A graph is shown labeled transition state. The y-axis on the graph is labeled energy, and the x-axis is labeled extent of reaction. Two curves are plotted on the graph. Both start midway up the y-axis. The red curve has a steep initial slope as it increases, then reaches its peak where it meets a horizontal dotted line, then has a steep decline before leveling out. From the initial point to the horizontal line, there is a vertical line with arrows on each end labeled E subscript forward. From the end point to the horizontal line, there is a vertical line with arrows on each end labeled E subscript reverse. The second curve is less steep than the first and does not reach as high of a peak on the y-axis. It meets a separate horizontal dotted line at its peak, then declines at a similar rate to the first curve before leveling out with the first curve. From the initial point where the slope begins to increase to the horizontal line, there is a vertical line with arrows on each end labeled E subscript forward. From the end point right as it levels out to the horizontal line, there is a vertical line with arrows on each end labeled E subscript reverse. Figure 13. 8 reaction diagrams for an elementary process in the absence red and presence blue of a catalyst. The presence of catalyst lowers the activation energies of both the forward and reverse reactions, but does not affect the value of the equilibrium constant. An interesting case study highlighting these equilibrium concepts is the industrial production of ammonia, NH3. This substance is among the top 10 industrial chemicals with regard to production, with roughly 2 billion pounds produced annually in the U.S. Ammonia is used as a chemical feedstock to synthesize a wide range of commercially useful compounds, including fertilizers, plastics, dyes, and explosives. Most industrial production of ammonia uses the Haber-Bosch process based on the following equilibrium reaction. N2 letter 1D454 plus 3H2 letter 1D4542 NH3 letter 1D454 delta letter 1D43B equals minus 92. 2 kJ. The traits of this reaction present challenges to its use in an efficient industrial process. The equilibrium constant is relatively small, Kp on the order of 10⁻⁵ at 25 degrees C, meaning very little ammonia is present in an equilibrium mixture. Also, the rate of this reaction is relatively slow at low temperatures. To raise the yield of ammonia, the industrial process is designed to operate under conditions favoring product formation. High pressures, concentrations of reactants are used, 150–250 atm, to shift the equilibrium right, favoring product formation. Ammonia is continually removed, collected from the equilibrium mixture during the process, lowering its concentration and also shifting the equilibrium right. Although low temperatures favor product formation for this exothermic process, the reaction rate at low temperatures is inefficiently slow. A catalyst is used to accelerate the reaction to reasonable rates at relatively moderate temperatures, 400–500 degrees C. A diagram illustrating a typical industrial setup for production of ammonia via the Haber-Bosch process is shown in Figure 13. 9. A diagram is shown that is composed of 3 main sections. The first section shows an intake pipe labeled with blue arrows and the terms N subscript 2, H subscript 2, feed gases, and compressor. This pipe leads to a large chamber with a turbine in the top section and a coil in the bottom section. From top to bottom, the sections of this chamber are labeled heat exchanger, catalyst chamber 400 to 500 degrees C, catalyst, heater, and preheated feed gases. One pipe leads from the top of this chamber with red arrows and is labeled NH subscript 3 and unreacted N subscript 2, H subscript 2, while another pipe leads to the bottom of the chamber and reads compressor and has orange arrows going through it. These two pipes are connected to a square container that is labeled heat exchanger and has red arrows going into it from the upper pipe, orange arrows going away from it to the lower pipe and into a third system. The pipes leading into and out of the heat exchanger are labeled recycled N subscript 2, H subscript 2. The third system shows a container with an interior zigzag-shaped pipe that sits on a base that contains a curled pipe on a storage tank. From the top of the image to the bottom are the terms NH subscript 3 and unreacted N subscript 2, H subscript 2, condenser, cold water in, refrigeration, NH subscript 3, L, and storage. Blue arrows lead away from the base of this system and into the second system, while other blue arrows lead into the system from the right side of the diagram and back out of the same chamber. Figure 13. 9. The figure shows a typical industrial setup for the commercial production of ammonia by the Haber-Bosch process. The process operates under conditions that stress the chemical equilibrium to favor product formation. Learning objectives. By the end of this section, you will be able to identify the changes in concentration or pressure that occur for chemical species in equilibrium systems, calculate equilibrium concentrations or pressures and equilibrium constants, using various algebraic approaches, having covered the essential concepts of chemical equilibria in the preceding sections of this chapter. This final section will demonstrate the more practical aspect of using these concepts and appropriate mathematical strategies to perform various equilibrium calculations. These types of computations are essential to many areas of science and technology, for example, in the formulation and dosing of pharmaceutical products. After a drug is ingested or injected, it is typically involved in several chemical equilibria that affect its ultimate concentration in the body system of interest. Knowledge of the quantitative aspects of these equilibria is required to compute a dosage amount that will solicit the desired therapeutic effect. Many of the useful equilibrium calculations that will be demonstrated here require terms representing changes in reactant and product concentrations. These terms are derived from the stoichiometry of the reaction, as illustrated by decomposition of ammonia. 2NH3, letter 1D454, N2, letter 1D454, plus 3H2, letter 1D454. As shown earlier in this chapter, this equilibrium may be established within a sealed container that initially contains either NH3 only, or a mixture of any two of the three chemical species involved in the equilibrium. Regardless of its initial composition, a reaction mixture will show the same relationships between changes in the concentrations of the three species involved, as dictated by the reaction stoichiometry. See also the related content on expressing reaction rates in the chapter on kinetics. For example, if the nitrogen concentration increases by an amount x, delta N2 equals plus, letter 1D465, the corresponding changes in the other species' concentrations are delta H2 equals delta N2 equals plus 3, letter 1D465, delta NH3 equals minus delta N2 equals minus 2, letter 1D465, where the negative sign indicates a decrease in concentration. Example 13. 6. Determining relative changes in concentration. Derive the missing terms representing concentration changes for each of the following reactions. Acetate H2, letter 1D454 plus letter 1D465 to Br2, letter 1D454 C2H to Br4, letter 1D454. B, I2, letter 1D44, letter 1D45E plus I minus, letter 1D44, letter 1D45E. 3 minus, letter 1D44, letter 1D45E, letter 1D465C. C3H8, letter 1D454, plus letter 1D465 502, letter 1 d454 3 code 2 letter 1 d454 plus 4 h do letter 1 d454 solution a seat h2 letter 1 d454 plus letter 1 d465 to br2 letter 1 d4542 letter 1 d465 c2 h to br4 letter 1 d454 minus letter 1 d465 b I2 letter 1 d44e letter 1 d45e plus minus letter 1 d465 I minus letter 1 d44e letter 1 d45e minus letter 1 d465 I3 minus letter 1 d44e letter 1 d45e letter 1 d465 c c3 h8 letter 1 d454 plus letter 1 d465 502 letter 1 d454 5 letter 1 d465 3 code 2 letter 1 d454 plus minus 3 letter 1 d465 4 h do letter 1 d454 minus 4 letter 1 d465 check your learning. Complete the changes in concentrations for each of the following reactions. A2 so 2 letter 1 d454 plus O2 letter 1 d454 letter 1 d465 2 so 3 letter 1 d454 B C4H8 letter 1 d454 2 seat H4 letter 1 d454 minus 2 letter 1 d465 C 4 and H3 letter 1 d454 plus 702 letter 1 d454 4 no 2 letter 1 d454 plus 6 H do letter 1 d454 answer A2x x minus 2x bx minus 2x c 4x 7x minus 4x minus 6x or minus 4x minus 7x 4x 6x calculation of an equilibrium constant. The equilibrium constant for a reaction is calculated from the equilibrium concentration or pressures of its reactants and products. If these concentrations are known, the calculation simply involves their substitution into the K expression, as was illustrated by example 13. 2. A slightly more challenging example is provided next, in which the reaction stoichiometry is used to derive equilibrium concentrations from the information provided. The basic strategy of this computation is helpful for many types of equilibrium computations and relies on the use of terms for the reactant and product concentrations initially present, for how they change as the reaction proceeds, and for what they are when the system reaches equilibrium. The acronym ICE is commonly used to refer to this mathematical approach, and the concentrations terms are usually gathered in a tabular format called an ICE table. Example 13. 7. Calculation of an equilibrium constant. Iodine molecules react reversibly with iodide ions to produce triiodide ions. 2. Letter 1d44e letter 1d45e plus I minus letter 1d44e letter 1d45e 3 minus letter 1d44e letter 1d45e if a solution with the concentrations of I2 and I minus both equal to 1. 0 times 10 minus 3m before reaction gives an equilibrium concentration of I2 of 661 times 10 minus 4m. What is the equilibrium constant for the reaction? Solution to calculate the equilibrium constants. Equilibrium concentrations are needed for all the reactants and products. Letter 1d43 letter 1d436 equals 3I2I minus provided are the initial concentrations of the reactants and the equilibrium concentration of the product. Use this information to derive terms for the equilibrium concentrations of the reactants, presenting all the information in an ICE table. This table has 2 main columns and 4 rows. The first row for the first column does not have a heading and then has the following in the first column: initial concentration, M, change, M, equilibrium concentration, M. The second column has the header, I subscript 2 plus sign I superscript negative sign equilibrium arrow, I subscript 3 superscript negative sign. Under the second column is a subgroup of 3 rows and 3 columns. The first column has the following: 10 times 10 to the negative third power, negative x, I subscript 2 subscript I minus x. The second column has the following: 0 times 10 to the negative third power, negative x, I superscript negative sign, subscript I minus x. The third column has the following: 0 positive x. I superscript negative sign, subscript I plus x at equilibrium. The concentration of I2 is 661 times 10 minus 4 m, so that 1,000 times 10 minus 3 minus letter 1 d465 equals 6. 61 times 10 minus 4, letter 1 d465 equals 1,000 times 10 minus 3 minus 6. 61 times 10 minus 4 equals 3. 39 times 10 minus 4, letter 1 d440. The ICE table may now be updated with numerical values for all its concentrations. This table has 2 main columns and 4 rows. The first row for the first column does not have a heading and then has the following in the first column: initial concentration, M, change, M, equilibrium concentration, M. The second column has the header: I subscript 2 plus sign, I superscript negative sign, equilibrium arrow, I subscript 3 superscript negative sign. Under the second column is a subgroup of 3 rows and 3 columns. The first column has the following: 10 times 10 to the negative third power, negative 339 times 10 to the negative fourth power, 661 times 10 to the negative fourth power. The second column has the following: 10 times 10 to the negative third power, negative 339 times 10 to the negative fourth power, 661 times 10 to the negative fourth power. The third column has the following: 0, positive 339 times 10 to the negative fourth power, 339 times 10 to the negative fourth power. Finally, substitute the equilibrium concentrations into the K expression and solve. Letter 1d43, letter 1d450 equals 3 minus 2i minus equals 3. 39 times 10 minus 4, letter 1d440, 6. 61 times 10 minus 4, letter 1d440, 6. 61 times 10 minus 4, letter 1d440, equals 776. Check your learning. Ethanol and acetic acid react and form water and ethyl acetate, the solvent responsible for the odor of some nail polish removers. C2H5OH plus CH3-CoH, CH3-CoH C2H, 5 plus H2O. When 1 mol each of C2H5OH and CH3-CoH are allowed to react in 1 L of the solvent dioxane, equilibrium is established when 13 mol of each of the reactants remains. Calculate the equilibrium constant for the reaction. Note: water is a solute in this reaction. Answer: Kc equals 4. Calculation of a missing equilibrium concentration. When the equilibrium constant and all but one equilibrium concentration are provided, the other equilibrium concentration, S, may be calculated. A computation of this sort is illustrated in the next example exercise. Example 13. 8. Calculation of a missing equilibrium concentration. Nitrogen oxides are air pollutants produced by the reaction of nitrogen and oxygen at high temperatures. At 2000 degrees C, the value of the Kc for the reaction N2, letter 1d454, plus O2, letter 1d4542 no, letter 1d454, is 4 1 times 10 minus 4. Calculate the equilibrium concentration of NO, G, in air at 1 atm pressure and 2000 degrees C. The equilibrium concentrations of N2 and O2 at this pressure and temperature are 0.36 m and 0.89 m, respectively. Solutions: substitute the provided quantities into the equilibrium constant expression and solve for NO. Letter 1d43, letter 1d450 equals NO2 N2O2. NO2 equals letter 1d43, letter 1d450 N2O. 2 no equals letter 1d43, letter 1d450 N2O. 2 square equals 4. 1 times 10 minus 4, 0. 0 36, 0. 0 0 89 square equals 1. 31 times 10 minus 7 square equals 3. 6 times 10 minus 4, thus No is 3. 6 times 10 minus 4 mol/L at equilibrium under these conditions. To confirm this result, It may be used along with the provided equilibrium concentrations to calculate a value for K. Letter 1D43 letter 1D450 equals no 2 and 202 equals 36 times 10 minus 420, 036, 0, 89 equals 4. 0 times 10 minus 4. This result is consistent with the provided value for K within nominal uncertainty, differing by just 1 in the least significant digits place. Check your learning the equilibrium constant Kc for the reaction of nitrogen and hydrogen to produce ammonia at a certain temperature is 6 times 10 minus 2. Calculate the equilibrium concentration of ammonia if the equilibrium concentrations of nitrogen and hydrogen are 4.26 m and 2.9 m respectively. Answer 1.53 mol/L. Calculation of equilibrium concentrations from initial concentrations, perhaps the most challenging type of equilibrium calculation, can be one in which equilibrium concentrations are derived from initial concentrations and an equilibrium constant. For these calculations, a four-step approach is typically useful. Identify the direction in which the reaction will proceed to reach equilibrium. Develop an ICE table. Calculate the concentration changes and, subsequently, the equilibrium concentrations. Confirm the calculated equilibrium concentrations. The last two example exercises of this chapter demonstrate the application of this strategy. Example 13. 9. Calculation of equilibrium concentrations under certain conditions. The equilibrium constant Kc for the decomposition of PCl5G into PCl3G and Cl2G is 0. 2.11. What are the equilibrium concentrations of PCl5, PCl3, and Cl2 in a mixture that initially contained only PCl5 at a concentration of 1 m? Solution. Use the stepwise process described earlier. Step 1. Determine the direction the reaction proceeds. The balanced equation for the decomposition of PCl5 is PCl5, letter 1D454, PCl3, letter 1D454, plus Cl2, letter 1D454. Because only the reactant is present, initially Qc equals 0, and the reaction will proceed to the right. Step 2. Develop an ICE table. This table has two main columns and 4 rows. The first row for the first column does not have a heading and then has the following in the first column: initial concentration, m, change, m, equilibrium concentration, m. The second column has the header, PCl subscript 5 equilibrium arrow PCl subscript 3 plus Cl subscript 2. Under the second column is a subgroup of 3 rows and 3 columns. The first column has the following: 1, 0, negative x, 1 minus x. The second column has the following: 0, positive x, x. The third column has the following: 0, positive x, x. Step 3. Solve for the change and the equilibrium concentrations. Substituting the equilibrium concentrations into the equilibrium constant equation gives letter 1D43 letter 1D450 equals PCl3Cl 2PCl5 equals 0. 2.11 equals letter 1D465, letter 1D465, 1. 0, 0 minus letter 1D465, 0. 0, 211 equals letter 1D465, letter 1D465, 1. 0, 0 minus letter 1D465, 0. 0, 0 minus letter 1D465 equals letter 1D465 2, x2 plus 0. 0, 211 equals 0. Appendix B shows an equation of the form x2 plus bx plus c equals 0 can be rearranged to solve for x. Letter 1D465 equals minus letter 1D44f plus or minus letter 1D44f. 2 minus 4 letter 1D44 letter 1D450 square 2 letter 1D44 in this case. A equals 1, B equals 0. 2.11 and C equals minus 0. 2.11. Substituting the appropriate values for A, B, and C yields letter 1d465 equals minus 0. 0211 plus or minus 0. 0211 2 minus 4 1 minus 0. 0211 square 2 1 equals minus 0. 0211 plus or minus 4. 45 times 10 minus 4 plus 8. 44 times 10 minus 2, square 2 equals minus 0. 0211 plus or minus 0. 2912, the two roots of the quadratic are, therefore, letter 1d465 equals minus 0. 211 plus 0. 2912 equals 0. 135 and letter 1d465 equals minus 0. 0211 minus 0. 2912 equals minus 0. 156 for this scenario. Only the positive root is physically meaningful. Concentrations are either 0 or positive. And so x equals 0, 135 m. The equilibrium concentrations are PCl5 equals 1. 0, 0 minus 0. 135 equals 0. 87 m PCl3 equals letter 1d465 equals 0. 135 m Cl2 equals letter 1d465 equals 0. 135 m Step 4. Confirm the calculated equilibrium concentrations. Substitution into the expression for Kc to check the calculation gives letter 1d43 letter 1d450 equals PCl3Cl2 PCl5 equals 0. 135, 0. 135, 0. 87 equals 0. 21. The equilibrium constant calculated from the equilibrium concentrations is equal to the value of Kc given in the problem when rounded to the proper number of significant figures. Check your learning. Acetic acid, CH3CO2H, reacts with ethanol, C2H5OH, to form water and ethyl acetate, CH3CO2C2H5. CH-CO, HC, H, OCH3-CO2C2H, 5 plus H2O. The equilibrium constant for this reaction with dioxane as a solvent is 40. What are the equilibrium concentrations for a mixture that is initially 0? 15 m in CH3-CO2H, 0. 15 m in C2H5OH, 0. 40 m in CH3-CO2C2H5 and 0. 40 m in H2O. Answer: CH3-CO2H equals 0. 18 m C2H5O equals 0. 18 m CH3-CO2C2H5 equals 0. 37 m H2O equals 0. 37 m. Check your learning. A10 L flask is filled with 1 mole of H2 and 20 moles of I2. The value of the equilibrium constant for the reaction of hydrogen and iodine reacting to form hydrogen iodide is 50. 5 under the given conditions. What are the equilibrium concentrations of H2, I2, and HI in moles L? H2, letter 1d454 plus I2, letter 1d4542 high, letter 1d454 answer. H2 equals 0. 6 m, I2 equals 16 m, high equals 188 m. Example 13. 10. Calculation of equilibrium concentrations using an algebra simplifying assumption. What are the concentrations at equilibrium of a 0? 15 m solution of HCN. HCN. Letter 1d44e, letter 1d45e, H plus letter 1d44e, letter 1d45e, plus Cn minus letter 1d44e, letter 1d45e, letter 1d43, letter 1d450 equals 4. 9 times 10 minus 10 solution using X to represent the concentration of each product at equilibrium gives this ICE table. This table has 2 main columns and 4 rows. The first row for the first column does not have a heading and then has the following: initial pressure, M, change, M, equilibrium, M. The second column has the header, HCN, a Q, equilibrium arrow H superscript plus sign, a Q plus CN subscript negative sign, a Q. Under the second column is a subgroup of 3 columns and 3 rows. The first column has the following: 0, 15, negative x, 0, 15 minus x. The second column has the following: 0, positive x, x. The third column has the following: 0, positive x, x. Substitute the equilibrium concentration terms into the Kc expression. Letter 1d43, letter 1d450 equals letter 1d465, letter 1d465, 0. 15 minus letter 1d465. Rearrange to the quadratic form and solve for x, x2 plus 4. 9 times 10 minus 10, letter 1d465 minus 7. 35 times 10 minus 11 equals 0, letter 1d465 equals 8. 56 times 10 minus 6, letter 1d440, 3 sig, figs, equals 8. 6 times 10 minus 6, letter 1d440, 2 sig, figs. Thus h plus equals cn equals x equals 8. 6 times 10, 6m, and hcn equals 0, 15, x equals 0, 15m. Note in this case that the change in concentration is significantly less than the initial concentration, a consequence of the small k. And so, the initial concentration experiences a negligible change. IF letter 1d4650, 15m, then 0. 15 letter 1d465, approximately 0. 15. This approximation allows for a more expedient mathematical approach to the calculation that avoids the need to solve for the roots of a quadratic equation. Letter 1d43, letter 1d450 equals letter 1d465, letter 1d4650. 15 minus letter 1d465, approximately letter 1d465, 20. 15, 4. 9 times 10 minus 10 equals letter 1d465, 20. 15 letter 1d465, 2 equals 0. 15, 4. 9 times 10 minus 10 equals 7. 4 times 10 minus 11, letter 1d465 equals 7. 4 times 10 minus 11 square equals 8. The value of x calculated is, indeed, much less than the initial concentration 8. 6 times 10 minus 6, 0. 15, and so the approximation was justified. If this simplified approach were to yield a value for x that did not justify the approximation, the calculation would need to be repeated without making the approximation. Check your learning. What are the equilibrium concentrations in a 0? 25 mNH3 solution. NH3, letter 1d44, letter 1d45e, plus H2O, letter 1d459 NH4 plus, letter 1d44, letter 1d45e, plus O minus, letter 1d44, letter 1d45e, letter 1d43c equals 1. 8 times 10 minus 5. Answer: O minus equals NH4 plus equals 0. 21 m, NH3 equals 0. 25 m.